Hi, everyone. Welcome to another edition of Cohere Labs in Conversation. My name is Daniel Souza, and I work as a research engineer on the Cohere Labs team. Today, I have the pleasure of introducing Shashwat Goel, a PhD candidate at the LSN Max Planck Institute. I'm super hyped to have Shashwat talk about some of his recent work, which I just heard won the best paper at the ICML forecasting workshop, which is not surprising. But funny enough, I actually don't know Shashwat from this work. I've been following his research for a while. I know him from another paper, which is also a really good paper from last year, which introduces this technique called answer matching. It's a really nice paper. I remember it because figure 3 from there is fantastic. Highly recommend you check it out. All right, but today, Shashwat is here to talk and share some of his work. And the title is Forecasting World Events with Large Language Models. I find this particularly interesting because we're now entering this era where LLMs are being deployed as agents on long horizon tasks. This is also something that we're very curious and actively researching at Cohere Labs, and we're looking at how agents can adapt at test time with new information. So the way this will work is we'll let Shashwat get started, but if you have questions, put them in the chat. We'll have time for them at the end. But if I think there's something that will benefit, we can always interrupt him. But yeah, with that, thanks for accepting the invite, Shashwat. Thanks everyone for being here, and the floor is yours.
Yeah, thank you so much, Daniel, for one, like the generous introduction, but also hosting this talk and inviting me for it. And I'm super excited to talk more about the work we've been doing in like this is with like a larger collaboration. We like to call it like the OpenForecaster project, because there has been like some industry interest in forecasting with language models over the last year or so, but not a lot of it is like open source. So I think one cool thing about like our work is that we do release like all the data code and are very happy to like collaborate with people and discuss things in the open. So without further ado, let me like get started, and I will talk about like 3 different works we did over the last 1.5 years on this topic. So before I begin, I guess like one thing I should clarify is that I mentioned that I'll talk about forecasting world events, which is a bit different from the kind of forecasting that traditional machine learning folks might be used to. Because traditionally in machine learning, what people do is that when they say forecasting, they usually mean predicting some numeric time series where you can predict future observations given like a large history of past observations, and you train like regression models and whatnot to do this properly. What we are excited by is slightly different. So one thing that you get with language models is that in some sense they have learned everything about the world, and you can ask them like open-ended free-form natural language queries, like for example, who would win the next election in any country that you care about, and they can give you language in, language out responses, and you can ask them to make forecasts of like a much broader form than just time series. I think there's like some interesting work in also using them for time series, but that's not what I'm going to focus on. And on the slide, I have like some examples from these prediction markets that have become extremely popular over the last year, like Kalshi and Polymarket. And I have like on the left, a recent screenshot from Kalshi that I took earlier today on some popular questions there, which are about US politics. And on the right, I have like an older screenshot from like about a year ago or like 6 months ago, I think, from Polymarket. And you can already see that the events that are covered here are more discrete in nature, in the sense that if you ask who will win a particular sports match, it's not going to be like a time series answer. It's a specific event in a moment of time. So and obviously like you can imagine that news, like news that comes out in natural language in like the recent past from on the web, this can be like very useful for reasoning about such questions, but it's a bit tricky how to exactly do that, and language models maybe out of the box don't do that super well. So we'll discuss about how we can train them to do better, and also how to evaluate them and so on. You might be wondering, like, out of all the tasks that you can do with language models, like coding, or these days people are interested in automated research and whatnot, why do you want to study forecasting? Well, the first answer can be that I think a lot of people think that this is like a good measure of intelligence, because to some extent, whenever you're predicting something about the future, it's a naturally generalization task because you can't memorize something that hasn't happened yet. And in that sense, like it's one of like the good measures of intelligence that we do have, and requires like reasoning about how the world will evolve, which is also like a form of world modeling, another buzzword these days. Now, I'll try to give you more scientific reasons for why I became very interested in forecasting when I was starting my PhD. So I mean, the way I motivated is that when I started my PhD, I was looking for challenging tasks that language models don't really necessarily have saturated yet, and are also like interesting in the sense that maybe we're not measuring progress on these capabilities yet. And what I realized was that forecasting is like an excellent example of this. So this table kind of summarizes this, and I'll go through the rows one by one. So broadly zooming out, I think like forecasting is a great example of real world reasoning under uncertainty. So if you think about what kind of reasoning do you do throughout the day and you spend most of your time on, you will realize that a lot of this reasoning is actually reasoning under uncertainty. So obviously some of you are probably also solving like coding challenges and whatnot. But especially people who don't code or who don't do math for a living, a lot of the reasoning they do is about, oh, like for example, maybe what should I wear today? Which in some sense is a question of what will people think if I wear this particular thing, and what do I expect my day to look like? Do I expect there will be some rain which changes what I should wear? So this is like a very trivial decision maybe that we take, which requires some level of reasoning about uncertainty. And then another, or like more broader questions could be, what career should I pick up? What is the next job I should do? What is the next project I should try out? All of these things require reasoning about first of all, decisions, but also under the hood, they require reasoning about how the world might evolve and which careers might be lucrative 20 years from now, or which projects might actually be impactful 6 months from now, and so on. So it's a very different, I feel like this is a very different kind of reasoning from what you get with traditional coding and math evals, because in these evals, you're often given like the fully specified prompt of exactly what you need to do. And then you just have to like go and figure out an algorithm and execute the algorithm, which is formally called as deductive reasoning. And forecasting actually involves more of inductive reasoning. I don't want to go too much into like the details of these terms, but that's maybe one way to separate them. And the other thing is that like a lot of research is focusing now on long context, because it's one of those unsolved problems that we haven't really fully figured out. Language models have maybe like a 1 million context length. And again, with long context benchmarks, there is a big problem, which is like, how do you even evaluate long context reasoning in a realistic, natural way? And one good thing about forecasting is that it requires searching over a large corpus of evidence and reasoning about a large corpus of evidence. And unlike many other evals where maybe measuring them is like subjective, forecasts actually resolve. So 3 months later, you will maybe know the answer to your forecast, which is like the ground truth. And then you can use that to judge your forecast. So there is a verifiable reward in the end. And I will also talk about how you can use this verifiable reward for RL. So those are, I think, the first two reasons why I think forecasting is an interesting capability to track complementary from existing evaluations. But also there are like other benefits, such as in forecasting, everyday new events happen. This allows you to keep getting new samples continuously. And again, like since these questions are about the future, if you're careful about contamination, then basically you can ensure that the model isn't just memorizing things and actually has to reason. And finally, we're sort of running out of tasks which models are bad at these days. And there is this whole effort going on making harder and harder benchmarks, especially like how do you measure like superhuman models. And one thing about forecasting is that it's really hard for humans while having a verifiable reward and while having all the benefits of being economically valuable and whatnot. And in forecasting, we don't really know what the ceiling is. So you can probably do a lot better than what humans do today and what models also do today. So in some sense, you can keep improving for a long time. And I think like if you completely solve forecasting, then that would be like really valuable. So yeah, these are some of the reasons I think that forecasting is scientifically very interesting. And obviously, like, these are all the positives. There are also some challenges with actually measuring forecasting with language models, which I will now get to. This is like work we did. This from a paper called Pitfalls in Evaluating Language Models, and Pitfalls in Evaluating Language Model Forecasters specifically. And I will highlight two of the main challenges that I think are the most important when it comes to this work. So to begin with, how do you evaluate a language model forecaster? So the idea is that, well, one way to do this, which is probably the ideal way, is that you can ask questions about the future today. So for example, maybe about the end of 2026 today. And then you can get the model's forecasts and you can wait 6 months. And then 6 months later, you will know the answers to these questions. And that's your evaluation for the language model's forecasts. Obviously, the problem with this is that this is a very slow feedback loop. So if you're developing a model, you probably don't want to wait 6 months till you know whether your current iteration was good enough or not. So what people usually do traditionally in forecasting across the board is that they do something called back tests, where the idea is that you assume your model has a knowledge cutoff of some sort where it can't access world information after time t. This is true for language models because they're typically trained up till a certain point. And then you can test the model between the last time that it had access to information and today. Because in this period, what you know is that you know the ground truth answers for events that happened in this period. And you can use that to get essentially extremely fast feedback loops. So let me, I mean, this is like broadly the setup. And obviously, like, the first concern you need to carefully handle is that of leakage, where you don't want to have this problem where future information actually leaks into the model and the model actually has access to the time after you thought it had access to knowledge. And essentially, it shouldn't actually be able to memorize or just find the answer with web search or something. So for example, this does happen if you just use DuckDuckGo API or Google API, where in the examples that I'm showing, you can search for just random dates, like October 7 and January 6. And one thing you should notice is that I have set this date cutoff on the API. So some APIs do allow like this date cutoffs on the web search. But the problem is that even when you set up this date, what happens is sometimes future information leaks in. So here, like in the first example, I set the date cutoff to 2021, but then the first link already talks about 2025 things because maybe the article got updated. The second link also talks about 20, So like that's one problem. And then if you come to the second screenshot, here I search January 6th. This is when the Capitol Hill riots in the US happened. And that they happened like 2021, but I set the date cutoff to 2019. And you can see again that the first link already talks about the 2021 Capitol Hill riots. Now, basically the search engines are not very reliable in terms of enforcing these date cutoffs. So this is something that you need to be careful about, especially because search is such a useful capability to retrieve evidence for language model forecasters, even like human forecasters, that you definitely want to have search, but then it's very tricky to be careful about leakage. And then the second problem sometimes is that, so a lot of, like, for example, prediction market questions have these binary questions where the answer is yes or no. So for example, this is like one question from a forecasting data set, which was, again, it's a back test. So it's about events in the past, presumably before the model's knowledge cutoff. And the question is, will Queen Elizabeth live to 100 years? And the problem is that if you're testing a model in 2025 and it knows that it's being tested in 2025, the answer to this question was obviously no, because the model, if it knows that the question is being asked to it and such a question has been resolved for us to be able to actually evaluate it, in this case, you can infer that that 100 years have not passed since Queen Elizabeth was born, so she probably died before she was 100. And we actually looked at one of the seminal papers in language model forecasting and found that 5% of the data set had this problem. And the second type of problem that you have with questions is that very often people want to create these synthetic questions where, like I mentioned, like you might have news after the model's knowledge cutoff, which talks about events that have already resolved. And then if you try to create forecasting questions out of this news, I'll maybe motivate later why this is like interesting. What happens very often is that the questions end up being very specific things. So for example, this like question about will a body be found, by the way, trigger alert, but yeah, will a body be found on this specific street, on the specific block in early November 2024? And again, if you're being asked such a specific question and you have like some awareness about the fact that you're being evaluated, you can probably guess the answer is yes, because yeah, like only then would someone create such a hyper specific question in some sense. And it's also like very difficult to forecast. So it's kind of a bad question. And again, like in another paper, which was one of the first ones to do these synthetic question generation pipelines, we saw that 90% plus such questions existed, which were like too specific to be asked and just basically were about events that obviously happened. So given all these challenges, you have to be very careful both when you evaluate and train language model forecasters. And now I will talk about how our work on like training this OpenForecaster model try to sidestep these challenges in some interesting ways. So the first thing we do to handle like this web search leakage concern is that we actually downloaded an offline corpus of news. So we took news articles from 50 plus sources from Common Crawl, and essentially we set up our own search pipeline, which was this Qwen3 8P embedding model that retrieves relevant chunks for like a search query, which in this case was the question itself. And the idea is that not doing web search allows us to like actually do proper date cutoffs where since this is like an offline snapshot downloaded from Common Crawl, we have reliable timestamps after which the article was not updated. And then we can do proper date cutoff retrieval. And this plot shows that with retrieval significantly outperforms without retrieval across a bunch of different models, showing that the search quality is high enough to actually be quite useful for the model. So that's one part. And then the second part is about the binary questions being hyper-specific or leaking the answer, or sometimes being obviously yes and sometimes being obviously no. And the way we circumvent this problem is actually we make the questions more open-ended. So instead of asking, will X person win the election, which can only be answered yes or no, we actually ask questions like, who will win the election? And let the model come up with the answer, which is usually like a short form answer in these questions. And one interesting thing about this is that, first of all, we somewhat solve this shortcuts problem where in binary questions, it's quite easy to guess the answer sometimes based on the question. Whereas here, like the model has to, like the model is not given any set of options. So it has to like generatively come up with the answer itself based on its own reasoning, which also provides more learning signal because every sample you get more than one bit of information. But also it's very interesting in the forecasting setting because in forecasting, you often want to like predict these things called unknown unknowns. And if you can do that, that's like really useful because in some sense, if you already had to choose from a set of options, you're not really going beyond the imagination of the person that created the question. Whereas in these more free-form questions, maybe you can predict like black swan events or like really hard forecasting questions if you like reason sufficiently enough. And in some sense, you can come up with like novel hypotheses once you make the questions more free-form. With the obvious caveat that like free-form questions are hard to grade. So this is where like the answer matching paper that Daniel talked about actually came from. Like we were doing this forecasting project and we realized to judge these free-form questions, we need to check whether we can use a language model, which if you give it like the reference answer, can it basically check if predictions match the reference answer reliably? And indeed, like in that project, we did show that models are pretty good at this because it's essentially a paraphrase detection problem. And then once you can check whether a guess was correct or not, then you can use proper scoring rules, which is something like from the forecasting literature. Essentially, what they mean is that if a model gives you a prediction and a probability, then you can check whether this probability is calibrated. So what I mean by calibrated is that if a model says that it has 70% confidence in its prediction, then it should be correct 70% of the time, which basically means that model does not have any incentive to lie or be overconfident or be underconfident about its predictions. And we essentially set up this Breyer skill score, which is a slight adaptation of what exists in the literature because we have this open-ended answer setting. But essentially, the idea is very simple. It's just that if the model's guessed answer is correct, then you want to incentivize having high probability. So your ground truth probability is set to 1, and you want the probability to be as close to 1 as possible. So you take the mean square error from 1 of the probability that's output by the model. And if it's wrong, then the ground truth probability should be 0. And you want to, again, like you penalize the square of the probability that the model outputs. So for example, if I give like a concrete example, if the model gives a wrong answer and it has a high probability, then it should get a big penalty. And this is what this score ensures. And similarly, if the model gives a correct answer with high probability, then we should give high reward. If the probability is low on a correct answer, then we should give a lower reward, and so on and so forth. And I guess the only thing you need to remember for interpreting the results I'll show you now is that the score gives you a value between -1 and 1. 1 is if you were correct and had the maximum probability. -1 is if you were wrong and had the maximum probability. And 0 is basically an abstention where you give 0 probability to your guess. Now, so this paper that we did was essentially about training language model forecasters. And the biggest challenge with doing that is that there is not a lot of data out there for forecasting questions and their answers, especially after the knowledge cutoff of the model. So one big constraint we have is that forecasting questions need to be after the model's knowledge cutoff, which gives you like maybe a few month period to actually create questions. And the prediction markets, for example, don't have that many questions in like a 2 or 3 month period. So you need some way to like mine more questions at scale. So I told you earlier that we can't really use real-time data because the events would resolve too late, and prediction markets don't have enough questions. And also, like, one other problem is that there's reasoning traces for high quality forecasting are extremely hard to find because it's very hard for humans. And maybe there are like some super forecasters which are considered to be better forecasters than others, but then like collecting the reasoning traces is going to be very hard because such a small population that actually like does forecasting for a living, for example, or at least officially, professionally does forecasting. So you essentially can't rely on having like human reasoning traces to SFT on, like do supervised fine tuning on. So the main challenge we had to solve was how to create such training data. And the way we do this is, again, like I briefly hinted at this, which is that you can get news articles after the model's knowledge cutoff date, and you can try to create these free-form questions from these news articles. And what we do is essentially ask DeepSeek V3 with like a bunch of guidelines to create 3 questions per article, and then we have a filtering pipeline to choose the best question among those 3. So in the end, we get roughly 1 question per article. And like I have an example of a real question from our OpenForecaster dataset that we released for training these models, which is who will be confirmed the new prime minister of Ukraine on July 2025. Note that like we were training and testing Qwen3 models back then, which had a knowledge cutoff of July 2024. So this question is actually after the knowledge cutoff of the model that we were working with. But yeah, so basically you can see that there is this free-form question with a short answer that we can use for judging. So we did this filtering pipeline, and what I show so what you can see is that we started with like 250K source articles, and then after a bunch of filtering to ensure that the questions don't have leakage, where like maybe the question doesn't directly hint at the answer and so on, we were in the end left with 62,000 questions. And this filtering was really important because if your training data has leakage, like the questions sometimes directly contain the answers and so on, then your model will just learn the shortcut of finding this leaked answer rather than actually reasoning about forecasting. And in this case, your performance will actually worsen with training rather than improving with training, which happens after filtering. And then once you do this properly, what you see is that, for example, if we start with Llama 3.18b, and then on the x-axis, we scale the amount of training data we use, we see that essentially we basically see this log linear trend that you very often see in like data scaling curves, where just by doing post-training, which I'll come to how we do this post-training in a bit. But what I just want to motivate is that being able to scale this data really matters for improving the model. And in fact, by being able to train on 50, like at 1,000 questions, we make this 8B model match DeepSeek V3. And then by the time we hit 10,000 questions, we've already crossed a bunch of frontier open weight models at the time. And this keeps on improving even at 50,000 questions. And if we went on for longer, it might have actually improved even more. So how did we do this RL training? We just use GRPO. So the idea is that you have access to like this reference answer. You can check whether the model's prediction matches the reference answer. And you can use the Brier score and the accuracy of the prediction using answer matching, like I mentioned before, as your reward to train this system. And you also, like in our pipeline, we also give the model access to some static retrieved information that it can use. And basically what we show is that starting from Qwen38B, which is on the bottom left of this plot, we can go to this purple OpenForecaster 8B model, which is our fine-tuned model. And across both like a test set that we created of free-form questions and also like a binary and MCQ test set that someone else had created and released before, we see like basically this 8B model now starts to match GPT-OSS 120 billion, which is like a much larger reasoning model from OpenAI. We also saw that in long-term forecasts where you can only measure consistency, for example, if you negate the question, then the probability should become 1 minus the original probability. We see like much more consistent long-term forecasts. And also like recently we tested the model on 2026 questions, like 1 year after it had been trained up to. And even then we continue to see like strong improvements. And the other interesting thing is that the calibration that we get, so on the right, I have like the calibration curve of the model. What you want, like I said, was that you should be on the y equal to x line on this plot where I plot confidence versus accuracy, because if 70% confidence is given by the model, then you want to be accurate 70% of the time. We see that essentially the Qwen38B model was overconfident, where its confidence was much higher than its accuracy originally. And we bring it closer to being calibrated and to the y equal to x line with our purple OpenForecaster model. And on the left, we show that this calibration training on forecasting actually generalizes to a bunch of other popular data sets like Simple QA, GPQA, and MMLU Pro, where the calibration of the fine-tuned model also improves out of distribution. So that's the first part, which is like training language models for forecasting. I'll also talk a bit about the second project, which is how do you actually test frontier models at their ability to adapt to new information over time? So the interesting thing about forecasting is that once you make a prediction, ideally you want to keep updating your prediction as you get new information. So you could imagine that maybe the model makes like a first prediction on January 1, let's say 2026 in the case of this paper. And then as new news articles arrive over time, you would want the model to update its predictions across the questions. So essentially, in this paper, what we did was we created FutureSim, which is like a simulation environment where the simulation is grounded in real-world events. And this part is like really important. So the idea is that in most simulations, you have like some sim to real gap because the simulation maybe has like mechanics that the developers hand wrote themselves. Or maybe like there's a user simulator model and so on. And these like are essentially not real world events. Whereas what we do is we take like real world news articles as they happened over time and make the model update its predictions on real world forecasts, again, on like real world questions and so on. And a couple of interesting things happen in the setup. So one thing we do is instead of now asking the model one question at a time and asking it to answer it, we let the model essentially choose what questions to update its forecast on. Because let's say on January 22, you got some new news. You probably don't want to update forecasts on every single question that exists in the forecasting data set. Maybe there are only like a subset of 10 questions that actually get updated based on this news article or like the news that you got on this day. So we should let the model choose what questions to update forecasts on. And this is something you would want in like a deployment forecasting system as well, where let's say on a prediction market, there are thousands of questions. You don't want to update all of them every time you see a new news article. So you should let the model explore the news itself and also like decide which questions to update on its own. And we essentially simulate this exact setup. So we don't tell the model which questions to update. We basically like run this many months long simulation. So in this case, like 3 months from January 1 to March end in 2026. The model keeps going further in the simulation by calling the next day tool, which whenever it thinks that it's done enough for the day, it can just call next day and move forward in the simulation. And we have a huge context corpus because we're downloading Common Crawl news, and the model can use the search tool to like make partial observations on this context, which keeps updating over time. And finally, we again have the freeform questions that I talked about earlier, with one interesting change that instead of letting the model only make one prediction at a time, so for a question like who would be the next TikTok CEO, which is like a question we have in the data set, maybe there are like 10 possible candidates. And so you want to let the model make a distribution over many possible candidates rather than just give one guess and one probability. And we show that basically you can use the same Brier score we had earlier with some modifications and still have like a proper scoring rule, which we use in this paper. So just to give a concrete example of how the model updates its predictions over time, here is like a GPT 5.5 trajectory on the Nepal election question. And you can see that over time, it saw these news articles come out. For example, it saw there were these protests in Nepal, which basically updated its predictions towards the winning candidate in the end, which was this guy called Balendra Shah. And you can see that in some ways, the models updates, especially like towards the end here, and especially on like the second best candidate, which is like these more transparent lines here, they are quite aligned with Polymarket. So you can look at the Polymarket crowd aggregate for some of the questions in our data set, and you can see that the human aggregate also like is not very far from GPT 5.5's predictions in the case of this question. And in the paper, we show that this is actually true for like a bunch of other questions as well, although there are some cases where GPT 5.5 is much worse than the human crowd as well. So this was just to give you a qualitative example of what's going on. And with that, like here, like are some of the results of testing frontier models as of recently. So we tested, GPT 5.5, Opus 4.8, GLM 5.2, DeepSeek V4 Pro, and the largest Quen model. And what we find is that if you look at, for example, the left plot, one interesting thing you see is that GPT 5.5 really updates its predictions over time and makes them more accurate, which is maybe not true for GLM 5.2. We actually see this interesting behavior where GLM 5.2 at some point realizes that it's getting its predictions wrong, so it just stops making too many predictions or like updated predictions in the simulation. To the extent that DeepSeek V4 Pro, even though it started worse than GLM 5.2, over time becomes better than GLM 5.2 in the simulation. And yeah, you can see that Claude and GPT 5.5 have like a positive Brier skill score, which means that their forecasts are more informative than not making any forecast, which is not true for like the open weight models. So the open weight models, while they are catching up in coding, they seem to be like lagging far behind in forecasting as of now. And the other interesting thing is that, I mean, it's a 3-month long simulation, which while we backtest and this runs in just like a few hours, GPT 5.5 has to basically make 4,000 tool calls over 25 plus compactions, which brings back this point that I made earlier about how you can test like really long horizon tasks and reasoning over like a large amount of retrieved information using forecasting. And then a bit to hone in on this test time adaptation point, if we want to like compare models purely at their ability to adapt their predictions over time, what you need to do is you need to set like a common set of initial predictions so that the model's inherent initial forecasting capability doesn't become a confounder. So originally in the plot, you saw that the model started at different points. Here we set them at the same point by making their initial predictions essentially Quen 3.6 plus's original predictions, which are like weak predictions. And we see that some models obviously like update their predictions to become better, but none of them crosses like this 0 Brier skill score point, which at least Opus and GPT 5.5 were capable of. So essentially the models get anchored to the initial prediction, and currently they don't seem to adapt their predictions sufficiently over time. We also show that if you disable access to memory, which is basically just write access to the file system, in our case, all models worsen. So the dashed lines are the without memory lines, and the with memory lines are the solid lines. And you can see that memory really helps. So in the memory, the model is writing lessons like, oh, over time it realizes that maybe it's getting some predictions wrong. So it will write that maybe I'm too overconfident on sports, so I should have less probability on sports in my predictions. And these are the kind of things that models do. And this actually helps the model. Some models actually improve their predictions over time because of these things. And like when you remove the memory, they sometimes even just start reinforcing the same prediction and becoming overconfident and uncalibrated. Finally, one other interesting thing is that, like I mentioned before, search is a very useful skill in forecasting. And I want to hone in on how important it is, because I think forecasting is a great setting to study search agents and search tool calling, and also like reasoning about retrieved information and reasoning about what queries to search for. So this plot just shows that first, if you look at the right side, we run the models with the ability to do agentic search, which means they can do like hundreds of search calls over a run. In fact, GPT 5.5 does 4,000 tool calls. And we show that replacing this with just like a single search query, like we did in the OpenForecaster project that I showed earlier, where we just did one retrieval, like this one retrieval setting is much worse than being able to do agentic search, where you can keep updating your prediction by making more searches. And also, like on the left plot, I show that the fact that we update our corpus over time, which is this blue bar, really helps compared to not updating the corpus over time. Because if you don't update the corpus over time, the model cannot really improve its predictions over time. So this just shows that adaptation is like really important in our setting, and search is like a very important mechanism for this adaptation. Finally, like we show some inference scaling results where higher reasoning effort, which is like the darker lines for GPT 5.5, leads to much higher performance. So the last result that I maybe want to touch upon is that you can actually do multi-agent research in FutureSim. And we show like a small instance of this, but it would be, I'm like really excited about people taking FutureSim and going wild with different forms of multi-agent research. So what we specifically show in the experiment in our paper is that you can basically do self-play with 3 copies of the same agent. So we take 3 copies of DeepSeek V4 Pro in the same harness. And what we essentially see is that if we do this multi-agent run, which is in red, and on the other hand, we do single agent runs as a control experiment, which are in blue, we essentially track the distance between the predictions of the agents over time, like as the simulation evolves. And one thing we observe is that in the multi-agent run, the agents, so they can't communicate between each other, but they can see the aggregate prediction, which is like the average prediction for each question in the current environment. And what we see in the reasoning traces is that they have this conformity effect, where they basically say that I should update my prediction towards the aggregate. And this shouldn't really happen, because the incentive in any prediction market, also in our environment, is that the agent should have differentiated predictions which have like some alpha over the market. But somehow right now agents just like to converge towards the same predictions when they're run together, whereas in the independent runs, they actually do diverge from each other's predictions. So with FutureSim, I think like the high level idea that I wanted to emphasize, and which is probably the motivation for this research as well, is that in a lot of ways, continual learning is already considered the next frontier, or like the next bottleneck to AGI in some sense. And obviously, continual learning can mean many different things. For example, it can mean updating knowledge over time and updating the model's beliefs over time. It can also mean seeking new knowledge by realizing what you don't know and actually making search queries and so on. And finally, it can also mean learning on the job, where as you see the outcome of tasks that you did, you might want to like take lessons and improve your strategy and so on. And all of these things are something we are able to test in FutureSim in one environment, which is usually very hard, because a lot of continual learning in tasks that people study often end up being about one of these 3, whereas in some sense, we try to measure all of them in one environment. With the caveat being that we didn't do any like fine-tuning or weight update experiments in this paper, though I think that would be very interesting going forward. Primarily because we like for weight update experiments, we'd have to use small models, which at least on the set of questions we started with were quite bad. So we only tested test time compaction style continual learning in the simulation results that I showed you. Why this is interesting is I think that continual learning uniquely requires realistic environments. Now, obviously, every capability, it's better to measure it on real environments than not real environments. But the thing with continual learning is that the main constraint you have is that you have finite memory, which could be in the parameters or in the file system or in the context and so on. And given a finite memory, you can't learn arbitrary things. Like you can't squeeze in and remember everything that you saw in the environment. And essentially, this means you need to know what to forget and what to remember. And to know that, you sort of need to model the environment and predict what you will need in the future in the environment. And this is exactly what humans do. We also like continually learn over time. We forget a lot of things that we basically don't remember most of the things that we experience in our life. But in some sense, our brain is remembering the things we need, maybe, and that's the heuristic we are using. And that's why you should actually test models in a realistic environment to see if they can model or build like a world model of real world events as society evolves over time. And forecasting is a great way to do this because, like we show in FutureSim, you can simulate model predictions and beliefs over time using the setup we created. Yeah, so to conclude, I think like obviously people would be interested in some, like what's the motivation going forward, both for the OpenForecaster project and me. And I think like one important thing is that the reason even in the beginning, I said that the reason forecasting is interesting is because it's a verifiable task for open-ended decision-making and reasoning under uncertainty. And ideally, you would want that if you're really like getting super intelligence, then it should not be super intelligence only in like coding and math and these fully specified exam style problems and so on. But it should also be like super intelligence in terms of helping us make better decisions. Like for a lot of life choices that we make, it can be useful to like seek advice from advisors and so on. And I mean, humans are irrational, right? This is like well known that humans have cognitive biases. And there is no reason why a statistical machine learning model needs to have the same biases. So in theory, you could make language models really good at having a world model of how society evolves and so on, which can help people make better decisions. And going forward, I'm pretty excited about actually connecting from forecasting to real world decision making and seeing how we can actually evaluate real decision assistance from the models and also like train models to be better decision assistants. One thing that came out yesterday that I want to shout out is there was this Inkling model release that you might have seen, where they focus, if you scroll down the blog, they focus a lot on epistemics, which is essentially like calibration and things like this. And they actually show that the model is really good at this. I also ran like some private evals that I have and found that the model is like really strong at forecasting and like just the ability to reason about uncertainty. So yeah, like these are just some excerpts from the blog, just to say that this is something that Frontier Labs have started to care about, and they are actually highlighting this in their releases because in some sense, they also realize that for a lot of queries that users ask models, it's about uncertain questions or like decisions that users want to make. And it helps to have like a model that is calibrated, is not overconfident, will accurately say it doesn't know something when it really doesn't know something, and so on, and not like mislead people. So yeah, that's my presentation. And like I said, we do open source everything. That's the whole point of the OpenForecaster project. So yeah, it would be great. Like I would really love it if people can use these resources and also like build on top of them. And we like, so this, yeah, Nikhil and I, who often lead these forecasting projects, we're very happy to like share notes or answer any questions. Yeah, thank you.
This was fantastic, man. Thank you so much. This was such a good talk. All right, I have a bunch of questions from reading the paper and now, but let's look at the questions that the audience has posted. So I think an overarching kind of theme is, I think a bunch of people are asking whether if we actually get it to make predictions, instead of actually making the prediction, is it possible to kind of point it back to features or information that has led it to believe that something will happen? Do you have any insights that you'd like to share there?
Yeah, I think that's a great question. So basically, if I understand the question, it's something like, instead of just giving like a guess and a number, can we also train the model to give good explanations? And I think this is really important, right? Because in forecasting, if you're testing a real system, and you're asking about like a career choice, you probably don't want to just buy a number and a decision that the model gives you. You maybe want to like actually understand why the model thinks so. Maybe you have some private information, or like your preferences diverge from what the model thinks and so on. So I guess all I can say is that it's a really important problem. I don't have like really strong answers on what is a good explanation. So I think measuring what is a good long form explanation is a really hard problem. And there's been like some traditional work on this, like I think back in BERT days and so on, but I haven't seen like a lot of work on this recently. And I think it's like a very interesting research question that I've spent some time thinking about. And if like people have thoughts, I'm also happy to like discuss them.
I think there's also, I mean, one one very realistic thing you can point to is when we're making a prediction, we're always kind of thinking about what we know about the world and then saying something. Here you have this model that's actually searching over a corpus of something and then making some call, right? And eventually, if you can look at which ones it's getting right and look at what data it's actually looking at, there's also some way to kind of look and see what it is referred back to. But I do want to say that I am very impressed that your slides are just a day old. Like you have the inkling stuff in there, which is excellent. Okay, I have a question. So I was thinking more broadly. So when you talk about forecasting, and I think you touched upon this earlier, when you're looking at something like coding, you have a very tangible benefit you can measure as you get better and better, right? And you do have like this oracle where you could build a system that solves every question. With forecasting, there's no real like you don't know what the end result can be. Like you can like maybe humans are actually terrible at it, and they pretty much are. But how do you kind of benchmark and see, okay, the model can get better? Like what are you actually measuring? Are you measuring search? Are you measuring compaction, adaptation, or just a retrieval of like text? Yeah, but the thoughts.
Mm-hmm. Yeah, I think that's a good question. So, so one thing is obviously that forecasting as a task is a mix of all of these capabilities. So there is like some amount of, like for example, search is very important, and within search, reasoning what to search about, reasoning about what information you already have, and then collect like if you get like conflicting perspectives, combining them into one coherent belief that you think is like the most accurate. So there are like all of these capabilities that, like you rightly pointed out, go into making a good forecast. And I think the best way to, in some sense, get a sense of what is like actually leading to more impact in improving your forecasts is just by running ablations. So I think that's like the benefit of having these backtest style evaluations, where, for example, here you can like we also have some evaluations where we just disable search and test the model. And we see that like really like a huge delta, even like if I go back in the slides to a much earlier version of this plot, which we did like 1 year ago with Retrieval, I think. Yeah, here. So you can see that even with like static retrieval, which is like just one retrieval query with 5 articles, there's a huge delta in forecasting performance. So in some sense, this tells you that search is like a very important lever. If you can do better search, that's going to give you big gains in forecasting. So so basically, like the broader answer being that ablations and just empirically measuring this is like really important. And then I guess like there was a second part to your question, which is how do you know where the ceiling is and whether the models are already like the best they can be? To some extent, this is really hard because obviously there is inherent uncertainty in future events and there's just some random noise. And you can't really know what the exact quantity of that is. There's probably like no way to find out except you try to train the best model you can and keep pushing forecasting capabilities. And at some point, maybe you really can't push them anymore. I just feel like we haven't hit that point yet. Purely based on like you can find that the models make dumb mistakes sometimes. They don't search enough sometimes. They get confused by like obviously wrong information from low quality sources. So all I can say is intuitively from working and like looking at the data, you can see that the models can be better right now. But I assume that at some point, if you keep pushing it, this will become like a big challenge.
Sweet. Okay. I actually saw something today that I thought I would love to get your thoughts on. So there's this tweet that's going viral. predicting who will win the FIFA World Cup, and it's from 2021, which says Argentina will beat Spain. And I'm sure this account has probably tweeted every possible combination and then they've deleted it. But what happens is all of this data kind of gets into the model and it's pre-trained, and then when you're generating questions also from these data sets, there's a lot of like high probability that these kind of facts also get in, right? How do you think, like, have you kind of thought about this, or yeah?
Yeah, so I think like again, the first part of your question brings up this thing that with forecasts, in some sense, yeah, you can like just predict, like register prediction about everything, and this can be like a failure mode. I think in language model evaluations, this is less true because you can literally ask the model to make one prediction and distribute probability from 0 to 1. So it can't really do this sort of fooling that a lot of human experts can sometimes do. And in general, obviously, like this is why people emphasize that you should look at forward tests of forecast. So essentially, people should pre-register their prediction, and they can pre-register only one prediction ideally, and then you can actually see what their forecasting performance is. So that's on the first part. I think this is like not probably like the biggest issue with language models, because you can observe exactly what goes in and what comes out, which may be not true for that Twitter account you were talking about. But the other part about yeah, so like can you does that answer your question? Or
So I think I was asking more about in terms of like it being present in the pre-training data, like
yeah, right, the training data.
always,
Yes.
yeah.
Yeah, so that's why again, like with the training, at least that we do, we focus on RL, and in the RL setting again, you can control like you have some forecasting questions in your training data, and these can be derived ideally based on like reliable news outlets. So obviously, you want to make sure that the events that you're targeting, they're like, it shouldn't be that the news article is actually an opinion piece and someone made an opinion. You can still maybe forecast what would this person's opinion be as registered at this point in time, but you shouldn't make the question around what was the ground truth at this point in time based on an opinion. So yeah, you just have to be careful about how you source your questions. And this is actually like a somewhat open problem in the sense that even though we set up this filtering pipeline, even then like the forecasting questions we created from this pipeline are probably not the highest quality. And you can clearly see there are issues. In our case, we just wanted something which is scalable for training, so we were fine with like slightly poor quality as long as performance improved. But you can keep up like improving this probability. Improving the quality of the questions, and that would probably keep giving you gains and a better forecaster. So yeah, I think it's just something you have to be careful about and has high reward in terms of like training a better forecaster.
All right. With judging these models in forecasting, I'd like to go back to your example about the Prime Minister of Nepal. So I think the date on there was July 17th, 2025, or something like that. When you're actually evaluating these models, how do you actually like weigh a prediction from July, say 17th, 2024 versus like a day before, which is June 31st, 2025?
Yeah, that's a great question. So one thing that I maybe sort of skipped over was that, yes, you're right that so in all the plots that I showed you the models forecast over time and the Brier score over time based on like the ground truth outcome. And maybe your question is essentially, how do you compress this time series of scores into one number? And I think there's like, again, like no ground truth answer here, which is like the best way to do it. But one very simple thing that you can do and actually works reasonably well is that you can just average the score across the days and just take that, or like sum the scores across days and take that.
But don't you have more information as you keep going?
Yeah, so you do have more information as you keep going. So you will see the number. Ideally, you want to see the number go up.
Yeah.
At the same time, essentially, if you just sum the numbers across the dates, then what you're saying is that you're equally weighting each day's prediction, and a forecaster that got to this prediction earlier would get a higher score earlier,
Right.
and would just be scored higher in this way. So maybe this is like not the best absolute calculation, but as a relative calculation for rankings, this is like probably good enough. And that's the assumption we use for now. But that's why I like to just show the full plot with the performance over time, because compressing to a single number obviously hides some of the information.
For sure, for sure. I was also really interested with like the plot that you showed, where even frontier models, if they start from bad predictions, like they don't recover. I'm wondering if you also tried the opposite, where you give like a bunch of predictions from a really good model and then see whether a weaker model you have. Okay, great.
Yeah. So this is again like a great question. We have in the paper, in the appendix, we have this plot. I don't have it on my slides, but what you see is something similar in the sense that obviously like you start from good predictions which are already above 0, and then what you see is that like models are able to improve on top of this as well, like they would in a normal simulation. And actually, one interesting thing is that even there you see that DeepSeek V4 Pro improves like as good as Opus and GPT 5.5, which is surprising because like its initial predictions were really bad, but it seems to be like very good at this ability to find new information with searches and update predictions over time. So this was, I think, like an interesting result where, and again, GLM 5.2 was also like bad at this. I think we have the result with 5.1, not 5.2, but 5.1, and I think even with 5.2, you'll see that it's not going to update its predictions a lot, which is just like a model behavior in some sense. And that's one interesting thing with these. There have been like a few other evals which have come out which study this like adaptation behavior recently. Like, for example, EdgeBench is one that I really like. And yeah, it's very interesting that some models adapt better than the others.
Sweet. Yeah, I think this setting especially kind of really tests and kind of separates one aspect of it in forecasting. But yeah, I would like to ask you to kind of, if you want to have like an open call in terms of what you'd like this project to be, how you'd like people to kind of take this and go ahead, and then we can end it from there.
Oh yeah, I think so. Coming to yeah, open directions. One obviously is like search. Like I mentioned, like if search is such high leverage for forecasting ability, then there should probably be like a lot of focus on training better search systems, and maybe the search community should do research on forecasting environments, because I think in some sense, from my chats with people who work on search, factuality is sort of saturated. Like at least frontier models are like really good. Once given access to search, they can find factual question answers quite easily, whereas in forecasting, it becomes more about reasoning about conflicting evidence and making searches based on uncertain information, which is like, in some sense, almost qualitatively different, even though they are like similar questions in form. So yeah, search is one. I talked about this multi-agent result. I think forecasting is a great setting for multi-agent, both self-play and also like cross-model play style of work, because again, like most of this work traditionally has focused on somewhat toy environments or like games and so on, whereas this makes it about like a real world task that people would care about. And then, yeah, like I said, in this work, we didn't do any like continual learning methods in the form of like weight updates. And I think like, again, continual learning literature, from talking to people, they seem to really be constrained by having access to real environments. And they end up doing like these sequential, like taking 3 random benchmarks and sequentially learning on them sort of settings, which are like not really how humans do continual learning, or like you would expect real world agents to do continual learning. So I feel like there's just a lot of scope in trying out continual learning methods in such an environment. And yeah, finally, I mentioned this broader vision that at least for me is like the most exciting, which is how can you go from a system that gives you like calibrated forecasts to actually helping people make better decisions, to which like one of the questions about explanations, I think brought one sub-problem of this broader decision-making problem as well. So yeah, how do you train better decision assistants, I think is like another like very important broader direction.
Sweet. Highly encourage everyone to read the paper. There's code available, data available. Thanks so much again, Shashwat, for joining. This was a really fantastic talk. And yeah, thanks everyone.
Yeah, thanks everyone for the time, and thank you for hosting, Daniel.
See you in the next one.